Good evening. Today we are going to see the design of flexural members. Before this, we are with videos where we have analysis of flexural members. When we will talk about design, we have to first decide the cross section, and after this, deciding this cross section, we are going to analyze it again. Means analyze. We have compulsory. It may be analysis or it may be design. Now, in this, we are with the first problem. You can see so design a simply supported beam of span 8.5 meter carrying a reinforced concrete floor on compression flange and the UDL dead load 12.5 kilonewton per meter and imposed load 27.5 kilonewton per meter. Act on the beam throughout the span. Assume FE 410 grade of steel. Now we are with first loading calculations as we have given dead load is given, live load is given. So we have dead load 12.5, live load 27.5, and then from this we will get total load that is equal to 40 kilonewton per meter. Span that is given, and the span is 8.5 meters. So we have 8.5 meters. And then from this we will get factorial load. So 1.5 into 40, that is 60 kilonewton per meter. And then we have 60 kilonewton per meter, RARB WL by 2, 255 kilonewtons. So we have SFD BMD. So whatever reactions that are shear forces, 255 kilonewton, and maximum bending moment WL square by 8, 541.88 kilonewton meter. Second step. First we have, you can see, first we have loading calculation, second SFD BMD. Then we will plot it. So we have second step. Third step, we have selection modulus required. Then ZPR required, M upon Fy gamma mm. Now, from which we got this formula that is not given in IS code. But if you remember, we have MD is equal to beta B Fy into Zp upon gamma mo. And then we require Zp. So M into gamma mo upon Fy beta B we have considered as 1. And then from this we are going to get ZP required 2384.27 centimeter cube. Now from this we are going to step 4, going to select the section ISMB 550, and then we have properties of this. D is 550, TF 19.3, TW 11.2, area 13211 mm square, BF, and then ZP R by. Then classification of section, which is from table 2, B upon TF, then 190 by 2 upon 19.3, and then we have less than 4.92, less than 9.4, so flange is plastic. Then D by TW, 550 minus 2 into 19.3 upon 11.2, 45.66, less than 84, therefore wave is also plastic, and therefore section is plastic. So because now after selection of section, whatever we are going to do over here, so we have selected this section for 2384.27, and now we are going to check it. This is actually, if you will see, this is for bending moment 541.88 kilonewton meter, and now we are going to check the capacity of this section, which should be greater than this. Then whatever section we have provided, that is satisfactory. So now, and so hence after we are going to get it as analysis. So from this analysis start actually. So analysis from this point. And then we have beta B equal to 1. Now shear strength VD Fy upon gamma mo root 3 HTW, and then we will substitute the value, gives me VD. Then we have zero point 0.6 VD, which will be 484.98, which is greater than 254 kilonewton, and we have low shear. And you can see for low shear, we have clause number 8.2.1.2. So when the factorial design force does not exceed zero point 0.6 VD, we have to find MD by using this formula. So we have, this will be MD is beta B ZP Fy upon gamma mo, and then we have that will be 616.36 into 10 raised to 6 Newton millimeter. So which is greater than 541.88 kilonewton meter. So this is this section is sufficient or can resist the load coming on it. So this is one problem. Then we have second problem in which we have given static moment at V 200 kilonewton, M 145 kilonewton meter, and we have so effective span we have given that is 6 meter. Now first we have SFD BMD. So here we need not require to go for loading calculation. So first step that is not here. So we have M is given, V is given. Then section modulus required, same step we have over here. So 145 into 10 raised to 6 upon 250 into 1.1. That gives me required ZP is 638 centimeter cube. Now we will go selection of section from IS 800 2007. We have this section, and then we have H equal to. Now again, from this selection of section or after selection of section, we have to go for analysis. For analysis only, we require all this data. Then we have classification. Same way we have to classify this section BF upon 2 upon TF, and that comes 8.42, which is less than 9.4. And the flange is plastic. Then we are in the same way, wave is also plastic. And therefore section is plastic section. Therefore beta B equal to 1. Then we have shear buckling is not checked because we have d by tw less than 67. That we require if we will go greater than 67. Then adequacy of section. That means whatever section we have provided, that section we have greater than required, and therefore okay. Now we have to check it shear strength, and then if you will see, we have this shear strength greater than 210. Sorry, actually this is we have 200 kilonewton only, not 210. So this is 200 kilonewton. So we have this also 200 kilonewton. So now as it is less than 200 kilonewton, so what will happen? So the check is of high shear. Now you can see this 8.2.1.2 for low shear, and this is for high shear. When the design shear force V exceeds zero point 0.6 VD, and it exceeds, where VD is the design shear strength of the cross section, and the design bending strength MD shall be taken as MD is equal to MDV. And from where we will get it? From 9.2. And now we will go for this 9.2. That page number 70 you can see over here. For plastic or compact section, we have MDV is equal to MD minus beta, MD minus MFD. Now beta 2V upon VD minus 1 whole square. MD we know as per 8.2.1.2, which is for low shear. We have factorial applied shear force. We have that is 200. VD design shear strength, which we have to calculate by Fy upon root 3 gamma mu H into TW. MFD plastic design strength of the area of the cross section excluding the shear area, considering partial safety factor gamma mu. And ZE we have elastic section modulus of the whole section. So we will now go for this. So we have this formula now, and then now we will go with this. So beta B ZP Fy upon gamma O comes 156.27 kilonewton meter. Beta 2V upon VD, so 2 into 200 upon 298.52 minus 1 whole square comes 0.15. And then we have ZFD, ZP minus AWIW, because they have clearly mentioned, if you can see this, then what they have mentioned over here, plastic design strength of the area of the cross section excluding the shear area. So we have to just exclude the shear area, and then we have that shear area which is AW into YW. Now actually section is 325, so that total we have considered 325 into 7. So we have actually, if we will go this exact, then we have to subtract that flange from both sides. But on safer side, we have considered total, that is 325. That wave which is in flange, that also we have considered. So this will be 325 into 7. So we have to actually, when we will go for plastic section, we have to divide it into 2. So we have this 325 by 2 and this 325 by 2, and we have to take at center. So what we will get then this, so center of this, so this distance we will get 325 by 4. So we will get it as 2 times 325 by 2 into 7 into 325 by 4. So 2 times means we have to take moment of this about center. And similarly, we have to take moment of this about center. And therefore, 2 gets cancel, and we have directly written it as 325 into 7. And this is into 325 by 4, and that will gives me value of ZFD 502.76 into 10 raised to 3. And from this we will have MFD as ZFD Fy upon gamma MO, which will be 114.26 kilonewton meter. And then we will find MDV, which will be MD minus beta, MD minus MFD, and then we have substituted this value, and this value comes 151.23, that is kilonewton meter. And this 151.23 kilonewton meter, which is greater than 145 kilonewton, and therefore safe. So a small change, if we will calculate percentage change in MD and MFD. So we are very less, that is around 2, 1, so 5, so 1.5, and then we have around 3, 3.2. Likewise, we have reduction due to high shear. So this is all about your design of laterally supported members. And in this, we have taken both the problems, one that is with low shear and another with high shear. So today we will stop here only. Thank you.